Hello, my name is Ivan Borisov. I'm from ITMO University, and this is the first video lecture for the module Simulation of Robotic Systems. So let us dive into the slides. So the module is called Simulation of Robotic Systems, and our primary task for today is to understand what does simulation means and why do we actually need it. And before this question, I also would like to tell you a little bit about the module structure. So before we dive into the material of this module, I would like to tell you about myself and about the motivation of the course module. All right, so I work at ITMO University for several years now, and I'm a researcher at the biomechatronics and energy efficient robotics lab here at ITMO. And my primary topics are grasping devices and ledger robots. So before university, I worked at industry, and here you can see a couple of grippers that I designed. So when I became PhD student, I also chose the same topic, grippers, for my thesis. So here you can see the device that I developed when I was a PhD student. It is a gripper, which is able to do the both fundamental type of grasp as a precision type of grasp on the left and the adaptive envelope type of grasp on the right. And here you can see that it is not a physical prototype, it is a simulation model. And I have done it before creating a physical prototype, such as I will be confident in the design. So here we can see the physical prototype, and it also is able to do grasping of different physical objects. And here you can see actually the whole motivation of the module. So if you want to be sure that your design is okay and it's going to work, before creating a physical prototype, we do need to make a simulation model, and we can verify mechanical design or control algorithms and maybe a different kind of aspects of robotic system to be designed. The grippers are not the only example. Here you can see another simulation of ledger robots. So here you can see different kind of legs designed for galloping robots. So you can see here that we studied where should we put a spring, such as the leg will be fast. And we did this simulation before creating a physical prototype that you can see here. This hopping robot is able to jump in a place, and it's able to run. It's not the only physical prototype. Here you can see our new design, hopping robot. So it's a very simple one. So it's like a 1D example of a hopping robot. So it's not able to run, it's not able to do something useful for now. But here our task was to create a very light, a very energy efficient robot, such as we can use a very low power motor to actuate this thing, right? So here you can see that we use a dynamical servo to activate this tiny robot, and it became possible to activate the robot because of the proper mechanical design. So we optimize mass distribution and elastic elements allocation, such as the mechanical design do most of the work. And the purpose of actuator is just to compensate energy that have been dissipated to heat because of the impact with the ground. And as you can see here, it's able to do the motion. And before creating a physical prototype, we did very elaborated simulation models. So we optimized mechanical design, we optimized mass distribution and elastic element allocation, and also we optimize and tune control parameters as well. So here you can see the main motivation that we need a lot actually simulation. And one particular example that I would like to maybe give more details about that. So we work with the Sber Robotics laboratory, and we had a project which basically is all about creating a new alternative group design for a gripper. So ICAP is humanoid robot child, and it has very dexterous, great robotic hands, but it's not very payload, it's not very robust. And we was thinking, is it possible to create another kind of gripper that will be maybe more robust and is able to grasp heavier objects? The problem with the grippers is that if it's very highly articulated dexterous hand, you need a lot of motors and you need to locate it somewhere. And here you can see a huge box with the motors. And we cannot use the same method for small humanoid robot. So we don't want to change another kind of parts of our arm. So we need to locate all the motors inside the palm. So this is the main constraint here, is the main restriction, that we need to create the gripper that we will be able to attach to the ICAP robot without this huge box with the grippers. All right, so we come up with with the design procedure. How can we synthesize fingers and digits for humanoids grippers, artificial hands, such as you need only few motors to steer them. So here you can see a design procedure steps. I do not want to give a lot of details here because it will be pretty long, but it's not the point. Here is the point that all synthesis has been conducted in MATLAB. So here you can see one index finger with the two phalanges, and actually to actuate this thing you need two motors. And our task was to come up with the linkage for a finger, such as we can use only one motor to actuate this thing. So we once again come up with the idea, how can you attach additional links with the elastic elements, such as it will be able to do precise pinch and grasp and adaptive encompassing type of grasp as well. So here on the right, you can see a final linkage structure, and here you need only one motor to steer the whole thing. And it's able to do adaptive grasp as well. And the adaptivity only because of mechanical structure. So we do need here two motors. So the only one motor, and the rest of the control is taken fully. It's all about mechanical structure, yes. So and the main point here is that we did it. We did all the steps, all this design procedure in the simulator that we're going to use in our course. So here you can see the CAD design of a gripper, and the main feature is that it has 14 degrees of freedom, and we need only 4 motors to activate this thing. So here you can see a small video with a physical prototype. So one motor we use to activate index and middle fingers, the second one for the middle and little fingers, and 2 motors for the thumb. And it's able to grasp whatever we want because it's highly underactivated and highly adaptive gripper. And here you can see that it's able to grasp different kind of objects. Yeah, and it was possible to synthesize the linkages and to come up with such complex mechanical design because we used a lot MATLAB. All right, so when there is a task to create something new, you start with some idea. For example, here it is our idea of using variable length links. As you can see here in this tiny animation, the green one, it's like a link that consists of actually 2 small links that connected to each other through a prismatic joint with a spring. And because of this idea, because of this concept, it's able to adapt to a shape of the object without additional motors and without additional control. So this is the idea. Then you do design, for example, CAD design, you do some analysis, you do some testing, virtual testing, you build a physical prototype, you test it, and then you understand that something maybe you can do better. You design another kind of version, you build it once again, you test it once again, and maybe after that you can find more disadvantages maybe, and you can iterate, and the number of iteration can goes to infinity. Here, the primary task, I believe, is to reduce a number of iterations, such as you can come up with idea, you do design, you optimize all the parameters before creating a physical prototype. You build it only like you create the physical prototype after optimization, and after that you do not need to create another prototype, because you already come up with a beautiful and optimal solution. And in order to find this optimal solution, you need to use optimization. And in order to do optimization, you need to understand well your system, and simulation will help you with that. All right. So I believe that all of you have different backgrounds. So I asked in-class students about their background, and from here you can see answers. And my task is to create a model that will be great for all of the students, no matter of your knowledge and your prerequisites. So here you can see that we do have a lot of diversity. All right, so finally, let's consider what is this module is about. So it's all about some principles. How can we do simulation? What is the difference between modeling and simulation? I would like to give you some insights on multi-physics modeling, and I will explain you what are the bone graphs and how actually can we do how computers are able to do simulation models, simulators, excuse me. MATLAB is not just a black box with the magic. And we'll consider bone graphs as I guess primary method to create simulation models. It's very powerful tool, and I believe that it is the main method which is used for simulators. So then after we consider bone graphs and the third and fourth lectures, we will consider also screw theory and Lie groups. It is a tool which is needed to describe motion of rigid bodies in Euclidean space. Actually, not only rigid bodies, but you also can use it for elastic elements, but it will be more advanced. So we will stick with the rigid body motions. We will consider kinematics and dynamics and control. And we are going to use MATLAB Simscape for all our practice and projects. But during my lectures, I will also show you another simulation package, which is called 20sim, and it is needed to show you the how bone graphs works. So here you can see a video with KUKA robots, and while you're watching this, you can consider that those are pretty much complex systems, right? And during our professional career, we handle those complex systems, and we need to understand how does physical system works, right? We need to so we handle those complex dynamical system, and we need some tools to analyze how complex dynamic system works. We need tools to study how does they work. We want to predict the performance. We want to fully understand how does they work, such as we can optimize it. And also we want to control them, so we want to steer them. And all this possible analysis, studying, predictions, optimization, and steering, all of this is possible only because we're able to do math models. All right, so what is the difference between modeling and simulation? So modeling is the act of creating a model. So a model supposed to be as close as possible to the reality, but also it's supposed to be simple. A model, you can think about a model like an equation on a piece of paper that describe dynamics of your robotic systems. Or maybe you can consider a model like CAD model with the shapes. Maybe you can think of models like a plastic toy of a building. It's also a model. So modeling is the act of creating this kind of model, but simulation is the act of using a model to study behavior and performance of a system that exists or a system that you design. So you use this simulation to study characteristics. You use it to understand how a system works. You use it to predict how it's going to behave. You use it for evaluation of a system. And sometimes you're not able to do a physical testing, right? So we'll consider this in later, but you can think like there's a systems, let's be general, like let's assume that you want to study motion of planets and you're not able to do this in real life because of the time constant. You need to wait a lot to wait for some process in space because it's time consuming. And also two important concepts. It's verification and validation. And verification answer on the question, have we built the model right? So it's about the whole process. How did we, how have we done it? And validation answers on a question, have we built the right model? Is the result model, is it the right one? Okay, so let us consider some example. So let's assume that you have this kind of model with a mass on the spring with a damper, and you can come up with this earlier Lagrange equation of motion. You can derive it. You will get something like this. And right now we performed an act of creating a model. So we did modeling. But if we will going to use it to create a block diagram in Simulink, and then we will get some plots to study the performance of this mass spring damper system, this will be simulation. And you can use basic blocks in Simulink to create this simulation model. It's pretty easy task for the simple 1D system, but it will be too difficult for more complex systems. And because of that, in this MATLAB, you also can find blocks like SimScape blocks, which basically are iconic representation of the same blocks as you can see here. And we will understand how does they work during our third lecture with the bone graphs. But here our point is that when you do deriving of equations, this one is modeling, and when you do a model to study behavior or performance, this one we will call simulation. So we need modeling as an act of creating a model for simulation to study behavior and performance of, in our case, robotic systems, and to do control also about the robotic systems. And simulation can be splitted on the verification and validation. All right. So basic principles. We want to create simulation models to predict future. I mean, we want to make sure that the system that we're going to create is going to work. I mean, if our task is to create a physical prototype, we want to make sure that our design is okay. And this is why we do simulation. We need to keep in mind that models, always models, they are restricted, and you need to understand how does it work, such as you do understand the limitation of your simulation models. So all the engineering and robotics are multidisciplinary, and this is why we also consider bone graphs as the tool to model multi-dynamics systems. And we will consider mechanical, electrical, and a little bit thermal domains as well. And also, another last point is that modeling and simulation prone to errors, and you need to keep it in mind. All right, so here you can think a little bit. You can pause the video and think about why simulation is better than a real system. It will be a great exercise if you will just pause the video and just consider this for a while. All right. The first advantage is that it's just cheaper to create a simulation model than creating a physical prototype. It's not always the case, but I believe it's a case in 90% of cases. Sometimes you cannot just do experiment in real life. So you can think here about maybe you want to, I don't know, to study your car, but you do not want to crash it against a wall, but you can do simulation model. Or maybe you want to study, as I already mentioned, motion of planets. And yes, you can wait 1 year to get all the data around about all the data about how Earth moves around the sun, but you can do a simulation model and get all this data in a minute. In the simulation model, you see all the aspect, and you can repeat it once again. You can smash a car against the wall like 1,000 times in a row with the different aspects. and to get all the useful data, and you can control everything. You can see everything, and time constant is not an issue for you anymore. And maybe the last point here is that some experience, just you cannot do this in real life because of the moral reasons. But also there is something, there's a disadvantages. You also can pause the video and you can think about for a minute. And the main disadvantage is that models prone to errors. It's pretty goddamn difficult to create a right, fully detailed model. So before you can get the results, you need to have a complete, validated, and a verified model. And another issue is the power of your computer. So we're going to use MATLAB, and I believe that MATLAB is the greatest program for simulation because it's pretty universal. You can do whatever you want. Yes, you can find maybe something more performance, but not such universal as MATLAB. So you can use MATLAB for mechanical design analysis, for the control systems, for machine learning, for technical vision. So you can use it, I don't know, for rocket science. It's pretty universal, and because of that, we're going to use it. And another point that ITMO University provide you with the license that you can install MATLAB, the entire MATLAB for free using your ITMO email. So you need to register yourself at itmo.ru. And if you get this ITMO account, you can register yourself on MathWorks website, and you will get your MATLAB license for free. About the course module, here you can see our plan for lectures. So there will be 10 lectures. This one is the very first one about the the differences between the simulation and modeling. So it's pretty much a warm-up lecture. The second one also will be a second introductional lecture about some issues in control and linkage synthesis. Then we will go deeper in the details, and we'll consider bone graphs as a method for multi-domain modeling and simulations. After that, we will consider screw theory as the way to describe configuration and motion of bodies in space. We consider kinematics, we consider dynamics, and we will finish it with the control. So with the first 8 lectures, I needed to do all the practice and projects. The 9th and 10th lectures are like extra material for those who are going to have an oral exam. And we will have 6 practice to accomplish 4 labs. So the first one is all about closed chain linkages and how can we tune a PID control to move this, to activate this closed chain linkages. Actually, this first lecture is all about the first experience in MATLAB. The second practice is a little bit more elaborated. How can we synthesize control algorithms for open chain robot? Then the third practice task is, you need to model and simulate very simple system, 1D system, but you need to create the whole simulation model from scratch. So you need to derive a math model. You need to derive a Euler-Lagrange equation to have a math model that then you can use basic Simulink blocks to combine them in a way such as you will create this Euler-Lagrange equation and create a simulation model such as you can study the behavior and performance. So like from scratch, without using Simscape multi-body blocks. And the final practice task will be all about the spatial robot, and here you will be needed knowledge. How can you describe motion of rigid bodies in Euclidean spaces, such as you can model the whole system and to create a model-based control system. So here you can see all information about the course, I believe. So you need at least to defend 4 practice tasks. So practice tasks, you need to defend them to get 60 points. 60 points is the lowest amount of points to pass the course. You will get a point. You will get mark E, and you're free to go. It's like if you will not be able to defend the practice task, you will fail the whole module. So each practice task costs like 15 points. Then the second stage is to defend the project, and you will get 30 points for this one. First of all, you need to come up with the project task. We will discuss it in details later. But basically, you need to stick with the robotic examples and consider your previous background and all the knowledge that you will get from creating practice labs to create something maybe more complex, like one huge project. And you need to come up with the whole task with aims, and you need to discuss it with me. And if you will do this before the 29th of October, you will get the maximum points here. Regarding the dates, I believe that I will change it a little bit, such as I will give you extra time for this. And then you need to do the implementation of the project. And the final part here is that you need to do a report and to defend your project. So more about the policy you can read in the syllabus. So if you defended all the practice labs, if you defended your project, and if your results are outstanding, you can get one extra point, such as you can get an A mark without oral exam, or if you didn't get all the points and you want to get an A, you need to pass the oral exam. So the ground rules is that the projects all must be focused on robotics. You can consider industrial, collaborative, variable, service, mobile robots. You can model the whole systems or just like submodels of the system, for example, actuators. I suggest you to use your previous background, such as you can create a nice, complex, huge project, and to get useful data. You can do this individually, or you can do this in groups up to 3 students. Your task is to come up with a relevant task. I will give you examples, and also when I will give you all the explanation about practice tasks, I will also provide you a rough list of tasks that can be used as a basis. So here you can see a couple of examples. So we can consider collaborative robots and variable robots. So it's like domains. And if we consider variable robots, here you can see modules and actuators for variable robots. So this one is variable stiffness actuator, which is called AVAS. And here we can see that it's able to interact with the external object gently without moving it, or it can change its stiffness and to interact with another cylinder rigidly. So here you can see another variable stiffness actuator, and those actuators are used for variable robots. And here you can see an example of how can we study not the whole system, but only a small part of it, like an actuator. Or here you can see another example of creating a model of collaborative robots. So for a pick-up-place operations, or to force interaction with some kind of objects. So those may be not very awesome. The visualization is pretty simple, but all the focus here is in control theory. So you need to come up with a math model of the spatial robots, such as you can do gravity compensation and impedance. You need to tune your impedance controller, such as your robot will be able to interact with the environment. And another example here is like an extra. If you want to go even deeper in the details and not to use blocks of like just use blocks in MATLAB without fully understanding how they works, but to create the whole model from scratch using just equations, and you can do all this modeling in 20th using bone graphs. So this multi-domain bone graphs. We will talk about bone graphs in our third and fourth lectures. So here you can see some animations with the different robots from previous courses. So here you can see a robotic gripper. Here also you can see a few robots. Yeah. So generally, regarding your project, you need to come up with idea. What do you want to model? I can give you a list of tasks, but I'm afraid that maybe the task that I will provide to you will be not very interesting for you, and this is why I'm give you this freedom to choose your own variant, to choose what do you want to model. You need to create this model, you need to conduct virtual experiments, you need to gather useful data, you need to reflect on it. And remember, there is no competition. You need only to unleash your creativity and unleash your imagination to get great results. So you can contact with me using email and Telegram. I believe that the basis of background, the background is all about basic mechanics, control, and linear algebra. It will be great if you know robotics, dynamics, and kinematics, but I will provide you all this information during the course. So for additional reading, you can consider those books. The first book, Modern Robotics by Kevin Lynch and Frank Park, is a very great book. I recommend you a lot. And there you can find everything that we're going to discuss except for bone graphs, or everything about kinematics, dynamics, control, spatial robotics. Then there is a mathematical introduction to robotics manipulations by Richard Murray, and basically it's the same stuff which is written in Modern Robotics book, but this one is more elaborated. And also there is a small book in Russian that I wrote. It's not about the theory like Lie groups and screw theory, but it's about how can you use MATLAB for multi-body dynamics. You can find the same information in the MATLAB documentation in English. So here you can see the whole list of books. Here you can see a list of additional video lectures. And thank you for your attention. That's it for now.